Section 3.4, Composition of Functions. To begin with, we have a definition of function operations, and we define here 4 different functions, new functions, based on 2 other functions, f plus g, f minus g, f times g, and f divided by g. By these relationships, f plus g of x is f of x plus g of x, f minus g of x is f of x minus g of x, f times g of x is f of x times g of x, and f divided by g of x is f of x divided by g of x. And this is true whenever g of x is not 0. We cannot divide by 0 still. And this is true whenever both of these functions are defined. So what we want to look at here is creating a couple of functions. Given f of x equals x minus 1 and g of x equals x squared minus 1, we want to find g minus f of x and g divided by f of x. And the question here is, are they the same function? So g minus f of x will be g of x minus f of x. So x squared minus 1 minus x minus 1, which, distributing the negative sign to the right and combining like terms, we should get x squared minus x, and then the negative 1 and the positive 1 cancel out, so x squared minus x. Next we will consider g divided by f of x. That would be x squared minus 1 divided by x minus 1 based on our definition of division. And this is true as long as g of x is not 0. So this is true for x not equal to 1. And that numerator factors as x plus 1 times x minus 1 divided by x minus 1. And of course, x is still not equal to 1. And so g divided by f of x is x plus 1 for x not equal to 1. Are they the same function? Pretty clearly they're not. We have x squared minus x and we have x plus 1. One has a domain restriction while the other doesn't. Okay, so be familiar with operating with functions in that way. Now, the 5th function operation we will discuss is composition. That's the focus of this section. The composition of functions is when the output of one function is used as the input of another. So, for any input x and functions f and g, this action defines a composite function, which we write as f with this little circle, f composed with g, such that f composed with g is f of g of x. G of x is the output, and so we're using that as an input for the function f. Now, the domain of the composite function, f composed with g, is all x such that x is in the domain of g and g of x is in the domain of f. Now, it is important to notice that the product is a different operation. We have 2 different things going on there. And we will come back to that finding the domain here in a few questions. So using the functions provided, find f of g of x and g of f of x and determine whether the composition is commutative. So f of g of x, for that, we will first write out what g of x is. So f of, and then g of x is 3 minus x. So the way this will work is everywhere that we have, just like with function notation, everywhere that we have an x in the function f of x, we'll replace that with 3 minus x. So this is 2 times 3 minus x plus 1. Distributing that, we have 6 minus 2x plus 1. Make sure that's clear. 2x plus 1. Now combining like terms, negative 2x plus 7. Negative 2x plus 7. So there's f of g of x. Now let's consider g of f of x. All right, well, f of x is 2x plus 1. Now we'll evaluate g of x at 2x plus 1. So this is 3 minus 2x plus 1. Distributing that minus sign, 3 minus 2x minus 1 And combining like terms, we get negative 2x plus 2. Now, if doing the operation f composed with g is the same as g composed with f, then it's commutative. However, we can see here that f composed with g and g composed with f are two different functions, so this is not commutative. Not commutative. And in general, function composition is not commutative. We cannot just simply change the order and get the same thing. Let's look at example 3. The function c of s gives the number of calories burned completing s sit-ups, and s of t gives the number of sit-ups a person can complete in t minutes. Now, we're going to assume that c composed with f, or c composed with s, works, okay, that it makes perfect sense, and we want to interpret c of s of 3. Well, s of 3 is sit-ups in 3 minutes. So then c of the number of sit-ups done in 3 minutes, okay, if that is sit-ups in 3 minutes, I'm going to write this out very plain, then this is the calories burned in 3 minutes by sit-ups. So the calories, once we input the number of sit-ups done in 3 minutes, that is the calories burned by those s of 3 sit-ups. So there we have it. Example 4, suppose f of x gives miles that can be driven in x hours, and g of y gives the gallons of gas used in driving y miles. Which of these expressions is meaningful? F of g of y or g of f of x? Let's just first write out what each of these is doing. Okay, so f of x gives miles, but its input is hours. All right, so x to f of x gives us hours to miles, and y to g of y. Okay, y is number of miles, and g of y is gallons. Gallons of gas. All right, well, tying these two together, f of g of y is going to take gallons of gas as an input. All right, so f of g of y is going to take gallons to miles. Well, then it's going to take, well, first it's actually going to take miles to gallons, and then from gallons, which no, f of x actually requires, okay, let's make a note of this. F of x requires hours as input. Okay, well, is g of y going to be hours? No, the answer is absolutely not. It is gallons. Okay, so let's make a note here. Okay, so the function f of g of y requires, or f of x requires we to give it hours, but instead we're giving it gallons. So that function is not going to be meaningful. All right, let's look at g of f of y, or g of f of x is the way it's written there. Okay. All right, well, f of x is going to produce miles, going to produce miles. G requires miles as input. So that actually makes sense. So this function would go from hours to miles and then miles to gallons of gas. Those units match up. All right, so let's go ahead and make a note of that. Hours to miles to gallons. And that is the process of g of f of x, and so that makes perfect sense. Let's rewrite that. Okay, that makes sense, so that means g of f of x is the meaningful one. All right, example 5. Use the table to evaluate f of g of 3. Okay. Well, first we're going to find what g of 3 is. Based on this table, g of 3 is 2. So this is the same as f of 2. And then f of 2 is 8. So that tells us that f of g of 3 is 8. Now in the other direction, let's see if we can use a different color for this. This is going to be g of whatever f of 3 is. Well, f of 3 is 3. And then g of 3 is 2, as we saw earlier. So g of f of 3 is 2. Next we're going to use this figure. We want to find f of g of 1. F of g of 1. So that means the input to g is 1. Input to g is 1. And the output, based on this graph, is 3. So let's go ahead and write that here. This is f of 3. Now we're going to take an input of 3 into the function f. If I find the input into f is 3, my output is this point, which is 6. So f of g of 1 is 6. Probably should have traced these over here to note that that is my output. All right, number 7. Given f of t equals t squared minus t and h of x equals 3x plus 2, evaluate f of h of 1. All right. So f of h of 1 first requires us to find h of 1. So over here on the side, I'm going to evaluate that. That is going to be 3 times 1 plus 2, which is 5. So this is f of 5. Now f of 5 is 5 squared minus 5. That's 25 minus 5, or 20. So f of h of 1 is 20. Now, as I mentioned earlier, we're going to discuss the domain of a composite function. This is going to be the set of all inputs x in the domain of g, for which g of x is in the domain of f. All right. What that means is if we are looking at f of g of x, two things cannot happen. Okay, we have to avoid two things. All right, let's see. G of x must be defined. G of x must be defined, and f of x must be defined. Now the second part is a little more tricky. Okay, so for g of x, we notice that we're dividing by 3x minus 2. Okay, so we need to make sure that is not equal to 0. Well, adding 2 dividing by 3 tells us that x cannot be 2/3. X cannot be 2/3. Okay, that value is not in our domain. Now next, we need to verify that this right here, x minus 1, is not equal to 0. Well, the input, however, in that function is g of x. So this actually necessitates that g of x minus 1, let's go ahead and put that, minus 1 must not be 0. That's where it gets a little more complicated. So bring that over here. That means that g of x cannot be 1. So let's find where it is 1. 4 divided by 3x minus 2 equals 1. Let's see, if we multiply by 3x minus 2 and then divide by 4, actually let's just multiply by 3x minus 2. 3x minus 2 equals 4. Now we'll add 2 to both sides, divide by 3, that'll be 6 divided by 3, x equals 2. So, going back here, that means that x cannot be 2. So we have found 2 restrictions. One, x cannot be 2, and x cannot be 2/3. So our domain, I'm going to write this in 2 ways. It cannot be 2/3 or 2. And in interval notation, that would be written as negative infinity to 2/3 union 2/3 to 2 union 2 to infinity. And that is our domain. And let's find this again with 2 different functions. To find the domain of f composed with g, where f of x is the square root of x plus 2 and g of x is the square root of 3 minus x. Okay, again we need to make sure that g of x is defined, which means 3 minus x must be greater than or equal to 0, which means x is, see, adding x, that'll be x is less than or equal to 3. Right, so x is less than or equal to 3. There's one restriction. Now we also need to make sure that g of x plus 2 is greater than or equal to 0, which means g of x is greater than or equal to negative 2. So let's solve this inequality. We're going to have square root of 3 minus x greater than or equal to negative 2. Or wait, that should be, actually let's not go any further than that. Let's go back to this statement. But that would always be true. Now the square root of 3 minus x is greater than or equal to 0. So therefore g of x plus 2 is greater than or equal to 0. So this is true always. We don't have to worry about that. The only restriction that we really have is making sure that x is less than or equal to 3. So our domain is negative infinity to 3, including 3. All right, now our last question. Write f of x equals the square root of 5 minus x squared as the composition of 2 functions. So we need to look for, as we've seen already, an inside function and an outside function. So one way to see this is, let's just say, let's call this h of x equals 5 minus x squared, and then g of x equals the square root of x. So you could view this as f of x equals, see, that would be g composed with h. We take our h of x function and plug that into g of x, and that would be our original function f of x. Another way to view that would be, let's take j of x, make two different variables, x squared, and then k of x is 5 minus x, in which case f of x, and these are two ways to write the same thing. That would be k of x composed with j of x, and that would be the same, have the same effect. Alright, that is the end of this section. So keep in mind that the inputs of a composition function, okay, what it does is it's taking inputs of one function, going to the outputs, and then taking those outputs and making those also inputs. Okay, so there's a big connection here. So let's just go ahead and write this. Okay, f of x takes f of g of x. Our x values go through g of x, and then those g of x's become outputs in f of g of x. This is the big idea here. Alright, that's the end of the section.